Now, before we get into today's lesson, let's take a look at the objectives from the CSEC chemistry syllabus. So, by the end of today's session, we should know the history of the periodic table and the contributions made by various scientists, specifically two, which we will get into. We should also explain the trends in group 2, the alkaline earth metals, in terms of their ionization energies and their reactivities. We should also explain the trends in group 7, which are called the halogens, in terms of their physical state and oxidizing strengths. And lastly, we should identify the trends in period 3, where the elements range from the metals in the form of sodium to non-metals in the form of argon. So, let's look at the periodic table. Now, several scientists have contributed to the general structure of the periodic table and how the elements are aligned in that periodic table. Now, one of these scientists is Dobrynin, and how he helped in the building of the periodic table. He only had access to about 50 elements at the time. He only knew of about 50 elements at that time. That is the early 1800s. And he realized that when he aligned the elements in terms of their increase in masses, he placed them in triads, and they called them the Dobrynin's triad. And he realized that the middle element, the mass of the middle element, was an average of the other two masses that are in the triad. For instance, one of his famous triad was the group 1 triad, consisting of lithium, sodium, and potassium. Lithium has a mass of 6.9, sodium has a mass of 23, and potassium has a mass of 39. If you should average 6.9 and 39, you would get 23. But this, it seemed plausible at the time, but it broke down over a longer period as more elements started to be discovered, and the system didn't work for those elements. So another scientist, Mendeleev, added to Dobrynin's work, and he aligned each element in terms of their masses. Now, Mendeleev knew of 63 elements at the time, in the mid-1800s, and he realized that when he arranged his elements in the fashion which he did, they tend to have similar properties within the group. So he came up with the grouping system: group 1, group 2, group 3. And for instance, group 1, we can see where lithium, sodium, and potassium, they have similar chemical properties. There were spaces in his periodic table, and he said that these spaces are for elements that have not yet been discovered. But based on what he's been seeing, he could accurately predict the chemistry and physical properties of these elements, which he eventually did. The problem with Mendeleev's periodic table was that he arranged the elements in terms of their masses. Now, that means that, for instance, carbon has carbon 12, carbon 13, and carbon 14. It has isotopes, and these isotopes have different masses. That means that each carbon isotope would exist in a different position in Mendeleev's periodic table. So his theory had to be reassessed and a new theory put forward. So the new periodic table came about, where we no longer arrange the atoms in terms of their increase in masses. We now use an increase in atomic number to assign each element a position in the periodic table. That means that all the carbon isotopes would be in the same position, because isotopes are atoms of the same element with the same number of protons but a different number of neutrons. So although the masses might vary, the atomic number would remain the same. So all isotopes of carbon would be in the same position, and the same for all the other elements. Now, let's look at the group 2 metals, the alkaline earth metals. Now, with the alkaline earth metals, they're group 2, meaning that they possess 2 valence electrons. So you can see where calcium is reacting with chlorine to generate calcium chloride. So essentially what happens is that the calcium metal donates the 2 electrons to the chloride, the chlorine, to form 2 chloride ions. Now, in order, reactivity of these group 2 metals is dependent on the ease at which the metal can give off those 2 electrons to a non-metal such as chlorine, right? So the easier it is for the metal to lose the electrons, the more reactive the metal would be. Now, if we should look here, we would see that the group 2 metals, they increase in mass as we descend the group from beryllium to barium. What that means is that in barium, the valence electron would be very far from the attractive forces of the nucleus, while with beryllium, the valence electron would be right next to the nucleus, so the attractive forces would be very strong. So in beryllium, it would be very hard to lose those 2 electrons. Therefore, since it's hard to lose those valence electrons in beryllium, beryllium would not be as reactive as barium. Now, it then says different reactivities due to the different size of the atoms, which I just explained, and the ionization energies decrease going down the group, meaning that as we move from beryllium to barium, the ionization energies get less, and that is because it is easier to lose that electron in barium because barium has a large atomic radius. Therefore, the valence electron is very far from the nucleus and can be easily lost with little energy. But with beryllium, you'd have to apply a large amount of energy to liberate those 2 electrons from the valence shell because they're so close to the nucleus. It then says, thus the elements become more reactive as we descend the group. Now, let's look at their reactivities with water. I'm going to read everything and then we analyze each situation. The first point says beryllium reacts with steam at high temperatures above 700 degrees to form beryllium oxide and hydrogen gas. The second one says magnesium burns in steam to form magnesium oxide, which is a white solid, and hydrogen gas. The third one says calcium, barium, and strontium all react with cold water with increasing vigor in an exothermic reaction. The metal hydroxide is generated in each case and an alkaline solution develops. Now, for the first one, it says beryllium has to be reacted with steam at 700 degrees. Magnesium burns in steam, not necessarily at 700 degrees, just steam, and the reaction goes. While with calcium, strontium, and barium, the reaction can go with cold water. What that says to me is that beryllium is not very reactive because in order to get it to react, you had to heat it to 700 degrees in steam. While with magnesium, it reacted with steam, but not necessarily at 700 degrees. It could be at a much lower temperature. While with strontium, barium, and calcium, the reaction, you don't need steam for those metals to react. You can just put it in some water and the reaction would be very vigorous, very exothermic, very rapid, right? You might have an explosion with these metals, right? So this proves that reactivity of these metals increases going down the group. And you can see the reactions here for calcium, strontium, and barium, they react with water and they generate the corresponding metal hydroxide. And it is this hydroxide that is responsible for the alkaline solution that develops, because we know that acids acids form acidic solution. They give off H plus to solution. But to have an alkaline solution develop, you need hydroxide ions, OH ions in solution. And that's why the solution becomes alkaline. Now, let's look at their reaction with dilute HCl. Now, it says that group 2 metals react with dilute HCl to generate the metal chloride in a colorless solution, and hydrogen gas is given off. And we can see the equation at the bottom, where X is just a group 2 metal, for instance, beryllium, reacting with HCl to generate beryllium chloride and hydrogen gas. And you can see the hydrogen gas bubbling out of solution in the form of effervescence, as effervescence is a rapid bubbling of a gas out of solution. So all the group 2 metals react with acid in the same way to generate the metal chloride and hydrogen gas. Now, let's look at the group 7 elements, halogens. So we might refer to them as halogens going forward and not necessarily group 7 elements. Now, so we're dealing with group 7 right now. So let's zone in on group 7. And it's from fluorine to astatine. Now, I should mention that astatine is the rarest element in the Earth's crust, the rarest naturally occurring element in the Earth's crust. And it is only formed from the nuclear decay of things like uranium and thorium. And the longest lasting isotope of astatine lasts about 8 hours. So it's very, very, very rare. So we won't have a picture to show you guys, but I'll show you iodine, bromine, and chlorine. Now, back to the lesson. So, as we descend the group from fluorine to iodine or astatine, the atoms become larger. They become less electronegative, and more intermolecular forces develop between the atoms, and I'll explain why. When we descend a group, when we descend any group, the atoms get bigger, right? So the size of fluorine to iodine, fluorine is very small while iodine is very big, right? Since iodine is very big, it comes into contact with other iodine molecules a lot more frequently. And we know how these molecules react with each other, because the last time we spoke about covalent bonding, we spoke about van der Waals forces. So when iodine comes into contact with another iodine molecule, you have these van der Waals interactions taking place. Van der Waals is a weak form of intermolecular attraction, but when you have a lot of van der Waals taking place, it adds up. So essentially, since iodine is so big, it has a lot of van der Waals interactions with other iodine molecules. It exists as a solids in the solid state at room temperature. While with something like fluorine, fluorine is very small. It is very rare when the fluorine atoms come into contact. When they do, it's just a simple van der Waals interaction and then they move apart. So fluorine exists as a gas. Chlorine exists as a gas as well for the same reason. Bromine is a lot bigger. Not as big as iodine, but it's bigger than chlorine and fluorine. Therefore, it exists as a liquid, while iodine has a lot of van der Waals interactions, causing it to exist as a solid. Mind you, it's not a rigid solid. It's very soft and easily broken apart, but a solid nonetheless. Now, you can see a picture of iodine in the corner, and it's a very soft metal, purplish, blackish solid. Not metal, sorry. A very soft, solid, purplish, blackish. And you can see bromine in the middle, being the liquid, the orange liquid, and chlorine gas, which is a yellow-green gas, which is toxic, that I should mention. Now, let's look at the oxidizing power of the halogens. Now, before we get into the oxidizing power of the halogens, there are some terms that I want you guys to familiarize yourselves with. So, you need to know oxidation, reduction, oxidizing agent, and what is a reducing agent. Now, an oxidation, before I get into the definition, the points highlighted in red, I want you guys to focus on that. Now, oxidation is the loss of an electron or hydrogen or the gain of oxygen by an atom. And it makes sense. If it's being oxidized, it should be gaining oxygen, right? Or losing hydrogen or electrons. Reduction is the opposite of oxidation. So it is the gain of an electron or hydrogen or the loss of oxygen by an atom or molecule. Now, what is an oxidizing agent? An oxidizing agent is any substance that causes the oxidation of another by the addition of an electron or hydrogen to itself, or the donation of oxygen to the other molecule. Right? So oxidizing agents oxidize other molecules and becomes reduced itself because it picks up an electron or hydrogen, but it oxidizes something else. Now, a reducing agent is the opposite of an oxidizing agent. So a reducing agent is any substance that causes the reduction of another molecule by giving that molecule hydrogen or electrons or taking oxygen from that molecule, right? So let's get into it. Now, so this is an example of a simplified example of oxidation and reduction taking place. We have sodium and bromine reacting to form sodium bromide. Now, initially, the sodium has no charge, and when it formed sodium bromide, we know that this is an ionic compound. And ionic compounds have ions in them. So this sodium exists as Na+. Since it exists as Na+, that means that it lost an electron. So essentially, sodium gave its electrons to bromine, right? And in so doing, sodium was oxidized to NaBr. Another person could look at it as bromine being reduced. So bromine accepted electrons from sodium and became reduced in the form of sodium bromide. Now, it says that as we go up group 7 from iodine to fluorine, the oxidizing power of the element increases. Now, what is oxidation? We just looked at the definition, and we said that oxidation is essentially a species, gaining electrons, right? In order to act as an oxidizing agent, you have to remove electrons from another species and add it to yourself. Now, if the oxidizing power of the halogens is increasing from iodine to fluorine, that means that fluorine finds it a lot easier to add an electron to itself versus iodine. And that is because iodine is a lot larger than fluorine. Since fluorine is so small, the valence shell is very close to the nucleus. Therefore, the valence shell is feeling a very high attractive force from the nucleus. So if a species is passing that has an electron, the fluorine atom can quickly pull that electron towards itself. So it essentially takes the electron from the other molecule and adds it to itself. In so doing, it oxidizes the other molecule, and it itself becomes reduced. So, this is due to the atoms getting smaller as we go up the group, and the effective nuclear charge increases, which I just explained. This makes the elements a lot more electronegative, and it becomes easier to remove an electron from another species, thus becoming reduced, but but oxidizing the other species in the process. So it's important to note that an oxidizing agent becomes reduced in the process. When it adds an electron to itself, it becomes reduced, but since the other species lost an electron, that species was oxidized. Now, so essentially this is what is happening. You have fluorine, well, the halogens, and you're adding electrons to them for them to become their ions. And we're saying that it is easier for fluorine to become reduced versus iodine. So fluorine is a stronger oxidizing agent than iodine due to the small size of fluorine relative to iodine. So the oxidizing strength increases up the group, but the reducing strength increases down the group. Now, why is that? Why does the reducing strength decrease going from fluorine to iodine down the group? And again, that is due to the size of the atom. Now, to be a reducing agent, you have to be able to reduce another species. How do you reduce another species? You reduce another species by giving that species or molecule an electron or hydrogen. In this case, we're focusing on the electron, right? So, it's the ease at which you can give off an electron to another species. So, fluorine, it's too small for the valence electron in fluorine, one of the valence electron in fluorine to be added to another molecule, because the nucleus is holding on to those valence electrons very strongly. But with iodine, the atom is a lot bigger. The attractive forces of the nucleus is not that strong on the valence electrons, so it's more likely for iodine to give off an electron to another molecule and reduce that molecule. So that's why we have that reducing strength increases going down the group, but oxidizing strength increases going up the group. Now, let's look at the trends across period 3. All right, so with period 3, you can see a gradual increase in the melting point for the first 3 elements, that's sodium, magnesium, and aluminum. And that is essentially because those are metals and the metallic bonding strength is increasing from sodium to aluminum. So I want you guys to focus on the green bars for now. And we can see that there is a gradual increase from sodium to aluminum. Now, sodium is a lot, the melting point for sodium is a lot lower than magnesium and aluminum, and that is because group 1 metals tend to be very soft. They're not hard to melt, right? They tend to be pretty soft. So, when we move from aluminum to silicon, we see a large jump in the melting point. Now, silicon is a non-metal. It exhibits covalent bonding, while sodium, magnesium, and aluminum exhibit metallic bonding. So one would expect that the metals would have a higher melting point and boiling point than the non-metal, which would make sense. But earlier I had mentioned that there are some covalent compounds that have higher melting and boiling points than metals, and that's because the type of covalent bonding that they display. Now, silicon displays something called a giant molecular structure, and it's similar to that of diamond, right? And it's this 3-dimensional structure where each silicon atom is bonded to 4 other silicon atoms in a tetrahedral type fashion. Now, this is a 3-dimensional structure. It's very rigid and very hard to break apart. That is why the boiling point and the melting point for silicon is so high, right? So, after silicon, we have the other elements, phosphorus, sulfur, chlorine, and argon. Phosphorus and sulfur, they also have interesting structures that I will touch on in the next slide. Chlorine and argon, these are very simple molecules, van der Waals interactions, and these melting points and boiling points are pretty low. But for silicon, although silicon undergoes covalent bonding, we did mention that it exhibits a different type of covalent bonding. It's a giant covalent structure, a three-dimensional structure, which is very different from that of chlorine and argon. So these are the structures for the molecules. At the left, you can see that that one is silicon, the three-dimensional structure, giant molecular structure, very rigid system, very hard to break apart. In the second structure, this is phosphorus, P4, right? And you can see that it has 3 phosphorus atoms bonded to each other, right? Now, this is a very strange system, and it is a very dangerous substance because this is white phosphorus. You have red phosphorus and yellow phosphorus. Red phosphorus is the phosphorus you see on the tip of matches, and this is very flammable. And this is white phosphorus. White phosphorus is even more dangerous than red phosphorus in that it ignites when exposed to air. You can just have it on a table and it just explodes. You don't have to touch it or anything. It just explodes. So white phosphorus, very dangerous. We also have sulfur, which exists in this crown-like shape, and it's a S8. Its molecular formula is S8, meaning that it has 8 sulfur atoms linked together in that fashion. Now, we are aware of chlorine and argon. Chlorine, 2 chlorine atoms bonded to each other, and argon is just a simple atom. And these are simple covalent molecules which have pretty low melting and boiling points. Now, before we end today's session, we should look at some questions. So that's exactly what we'll do. Now, the first question says, which of the following best explains why barium is more reactive than beryllium? A says the first and second ionization energies of beryllium is a lot higher than that of barium due to the large differences in their size. The second says the first and second ionization energies of barium is a lot higher than that of beryllium due to the large differences in their size. So essentially they switched the atoms there. C says the barium is more electronegative than beryllium, and D says beryllium has a larger atomic radius than barium. Now, the answer was A, and the first and second ionization energies of beryllium is a lot higher than that of barium due to the large differences in their size. And as I had mentioned before, beryllium is a lot smaller than barium. Therefore, the valence electrons are very close to the nucleus. So the nucleus has a very strong hold on those valence electrons. And for a molecule, for a group 2 metal to be reactive, it's the ease at which it can give off those valence electrons that determines its reactivity, right? So since beryllium, it does not readily give off its electrons, therefore it's not as reactive as something like barium, which is very big. Valence electrons are very far from the attractive forces of the nucleus. Therefore, they're weakly held and can be given off, and the reactivity would be a lot greater than that of beryllium. So the answer here is A. Let's look at the question 2. It says, what gas is produced when magnesium is reacted with dilute HCl? Is it CO2? Is it hydrogen? Is it oxygen? Or is it nitrogen? Answer here is B, hydrogen. So the H plus that the acid gives off in solution picks up the electrons from the metal and becomes reduced and forms hydrogen gas. Carbonates, later on you'll realize that carbonates generate carbon dioxide when you react those with acids. But when you react metals, whether it be group 1 or group 2 or group 3 metals, with acids, you generate hydrogen gas. Now, question 3 says, arrange the following in order of increasing oxidation power. And we have chlorine, fluorine, bromine, and iodine. And the weakest, so we should arrange it in the form of the weakest first and the strongest oxidizer last. Now, for something to be a good oxidizing agent, it should be able to abstract electrons from another molecule with ease, right? So the smaller the atom in this case, the better the oxidizing power or the oxidizing abilities of the molecule or atom. Now, we know that as we descend the group in the halogens, the atomic size increases. So fluorine would be the smallest, followed by chlorine, followed by bromine, and then iodine and astatine. Therefore, fluorine would be the strongest oxidant and iodine should be the weakest oxidant. So let's look at it now. Is it A, which has chlorine, fluorine, bromine, and iodine? So if we have iodine here, A is saying that iodine would be the strongest oxidant. But we know that this is not true, and we can rule out B as well, because it has iodine as its strongest oxidant. Now, we know that iodine is the weakest oxidant there, so it's either C or D. So C says iodine, bromine, chlorine, and fluorine, while D says iodine, bromine, and then it switches these two, fluorine and chlorine. I say that it is C in this order, where you start with the biggest atom and you end with the smallest atom. Now, the last question says, which of the following best describes an oxidizing agent? And it is B. It oxidizes other species in solution and becomes reduced itself.